We said that graphs were one way to characterize the state of matter, and we showed you the state of matter and its existence under different conditions in a pressure-temperature diagram. Similarly, we could look at state of matter in a pressure-specific volume diagram. In this case, this region here would be the liquid region. This region here under this dome would be the two-phase liquid vapor region, and this region here would be the vapor region. So the same material can be shown on a pressure temperature diagram, and we remember that this is the solid vapor line, this is the liquid vapor line, and this here is the solid liquid line. So now this line here is the line that shows you, that points to you the transformation from liquid to vapor at a given pressure. Similarly, I could show here the transformation from liquid to vapor at a constant temperature. This curve here represents again liquid to vapor transformation, but on a different diagram, on a pressure and specific volume diagram. So if I chose a constant temperature, just like I did here, I chose a constant temperature and changed the pressure, and I saw how liquid transformed into vapor. In this state, if I choose a constant temperature right here, and I start with a material right here that is described by this pressure P and a specific volume V at a given temperature. At the same temperature, if I reduce the pressure, just like I had reduced the pressure here at the same temperature, I would see that the pressure is reduced. The volume does not change significantly. So at the constant temperature, a significant change in pressure does not result in a significant change in volume, and we know that that is true with liquids. As we reduce the pressure at a constant temperature, the material stays in its liquid stage till it gets to this point. This point is the point of saturated liquid. At this point, we begin to see the first bubble. So the liquid begins to evaporate at this point. So this line here is the constant temperature, or the isothermal line. And at this point, the system begins to evaporate. This point is called the saturated liquid. Once we get to this point, there is no further reduction in pressure as the liquid becomes vapor. However, there is significant increase in specific volume. The material begins to expand without any change in pressure, and since we are following an isothermal line, without any change in temperature. Once it gets to this point here, all of the liquid has been transformed into vapor, and this is the saturated vapor point. Beyond this, any reduction in pressure causes a significant increase in specific volume, much more than we saw here. This here is now the vapor state. So we said that this line was an isotherm, it was at a constant temperature. We could draw another such constant temperature line, choosing a higher temperature, and we would find again that as the pressure was reduced, the specific volume would increase, but very little in the liquid phase, till we got to the saturated liquid point for this new temperature. At this point again, we would go through a transformation from liquid phase to vapor phase with a significant increase in specific volume till we got to the saturated vapor state, and from here again, reduction in pressure would cause a significant change in specific volume, a significant increase in specific volume in the vapor phase. So at a higher temperature, saturation pressure is also higher. Notice that this pressure, pressure of the saturated liquid or the saturated vapor, which is the same, is higher than this pressure. Also, the two-phase region, this region here is smaller than this region here. As we keep increasing the temperature, we'll find that these isotherms keep moving to regions of higher pressure, higher saturation pressure, and shorter two-phase regions, till we come to a point where there is almost no two-phase region. This point here is the critical point. At this point, we will see that the line will have no two-phase region, or almost no two-phase region, before it converts from liquid to vapor. Beyond that, we will not see any transformation at all, and this region here is the supercritical region. Thus, this pressure specific volume diagram shows us for a liquid vapor system the region or the conditions in which a material will stay in liquid, the conditions at which the system will be in vapor, the conditions at which we'll find saturated liquid at a given temperature or saturated vapor at a given temperature, the specific volume under these conditions, and so on. So we get to know the state of this material for different values of pressure, specific volume, or temperature by looking at this diagram here. Diagrams such as this, pressure specific volume diagrams or pressure temperature diagrams, give us a lot of information about the behavior of a certain material. In this case, we have expanded the liquid vapor phase behavior or the liquid vapor diagram for pressure specific volume graph to include the solid phase here, the solid to liquid phase transformation, so this is the two-phase solid to liquid, as well as the solid to vapor phase transformation. So such a phase diagram describes the conditions in which various phases exist, where they exist by themselves, where they coexist with each other. We can find out from diagrams such as this all information about a state of a pure material. We will find that such diagrams can also be used to represent mixtures of different kinds, systems where there are two or more components. We saw that the phase diagram could be drawn with respect to pressure, temperature, as well as pressure, volume. Notice how solid liquid or liquid vapor regions become phase transition lines. Remember that in a pressure temperature plot, we had the solid vapor line, the liquid vapor line, and the solid liquid line. This line here represented the liquid to vapor phase transition. So this point here was the point of liquid vapor transition at a given pressure and temperature. Now let's go to a pressure volume diagram. We remember that as the temperature goes down, you come to this point. This is the saturated liquid point. At this temperature here, the pressure doesn't go down any further, but the volume increases significantly, and then once you get to saturated vapor, as the pressure goes down, the volume also increases significantly. So notice here that we've gone from a point that showed us the transformation from liquid to vapor to an entire regional, a set of points, a line that shows us the transformation from liquid to vapor. Why is that? Why do we go from a point to a line when we go from a pressure temperature to a pressure volume system? The reason is quite straightforward. Notice that when a phase transformation happens, the temperature stays constant. Notice that this is the constant temperature line, and the pressure stays constant. However, what changes is the volume. There is a significant change in specific volume. In a pressure volume diagram, we are able to show this change in volume. In a pressure temperature diagram, both the pressure and temperature stay constant, and hence the phase transformation is a point. We are also able to see the critical point beyond which there is no difference between a liquid and a gas. We should be able to look at these phase diagrams such as PT diagram and PV diagram and be able to relate these regions in a PT diagram with the corresponding region in a pressure volume diagram. The diagram we choose to use, whether it's a PT diagram or a PV diagram, depends on what process a material is undergoing and the variables of interest for analysis with that process.